Okay, it's me again, Margaret. So this time, in this video, we're going to go over the practice problems. So I'm going to start, I've already done one of them on my board. Sorry, my computer is holding up my phone and it's going off. I've already done one of the problems on my board and I'll walk through it. And I'll do a couple of them from this one and then I'll go do one or two from the other handout, okay? So on this one, it's the practice problems 1 is how it's listed. So it's the one from the Germana. Do what, son? Mario. Just Mario? Not Hot Wheels Mario? Just Mario? Sorry, I have a sick kid at home. Mario. We're watching YouTube videos. Which one?
I want Mario and Mommy, I want that one. Hey, the one?
That one?
Yeah.
Okay.
Start.
Okay. Sorry. As you know from the previous video, my son is homesick from school today. So I'm letting him watch while I work on these. So you may hear him in the background. You may hear Mario or whatnot on my TV. So just know that. And thank you for your patience and understanding because he's not really a napper. So I doubt he sleeps during the day for me to get these done. So I'm just going to do it while I can. And so that y'all have it as early as possible. All right. So like I said, this is from the Germana problem set that is listed as practice problems 1. So let's look at the first problem where it says scale coloration. Sorry, guys. And I've already drank up my coffee. Awesome. Scale coloration of lizards has a complete dominance relationship where green scales are dominant over blue scales. Okay, so basically that's just saying green is dominant over blue. So you have 1,024 individuals that are homozygous dominant, 512 individuals who are heterozygous, and 64 individuals that are homozygous recessive. So none of that really matters other than you know that there are 64 individuals that are homozygous recessive, and you've got the population total. So what you have to do is you have to add up
Mommy, I don't like that.
1,024,
Mommy, I want it
512,
and that.
and 64. And that's going to give you a population total of 1,600. Okay? So you've got your population total of 1,600. And you know that
Race cars.
that one or that one.
Mario race cars.
I don't see that up there.
Mario race cars there.
That one?
No, Mario race
That one?
cars. I said Mario race cars.
Oh, I'm sorry. I forget my 5-year-old can read now. Sorry, guys. All right, Nathan. Pick, baby.
Monster Truck one.
That one?
Yeah.
Okay. All right. So, you know that 64 individuals have the homozygous recessive. So, what you do is you take the 64 and you divide it like by 1,600, right? So 64 over 1,600, and that equals 0.04. And so that gives you Q squared because you found the homozygous recessive frequency. 0.04 is Q squared. But in order to find P, you have to find Q. So what do? We square root. So 1024 plus 512 plus 64 equals 1,600. All right, so 64 over 1600 equals 0.04. So then what we do is we square root 0.04 to get Q, because Q squared is 0.04. So therefore we have to square both sides, or square root both sides, and Q is equal to 0.2. So then you take 0.2 and plug it into P plus Q equals 1 to find P. Okay? So 0.2 minus 1 is 0.8. So P is 0.8. So then you plug into your equation here. Why do I plug into this equation? Because it's that equation. P squared plus 2PQ plus Q squared equals 1. So 0.8 squared plus 2 times 0.8 times 0.2 plus 0.2 squared. So, okay, we simplify that. 8 squared, or 0.8 squared is 0.64. 2 times 0.8 times 0.2 equals 0.32. 0.2 squared is 0.04, which checks because that's what you found first, right? So I like to do this because I just like to have all of the variables listed out together. So then you add them up. 0.64 because it's P squared, plus 0.32 because it's 2PQ, plus 0.04 because it's Q squared is going to give you 1. And there you go. You found the frequencies. So the reason that we always do the homozygous dominant or the homozygous recessive when figuring out P and Q is because sometimes they don't give you the breakdown like they do in this one of which ones are homozygous dominant and which ones are heterozygous. Sometimes they're just going to tell you that this number of individuals has green and this number of individuals has blue. Okay, or this number of individuals is dominant, this number of individuals is recessive. Find the traits or find the frequency. So you always have to have the population total. That's the key. And as long as you know how many are showing recessive, you can figure it out. So you take the recessive number, divide it by the population total, and you're going to get Q squared. Because we know that no matter what, if they're showing recessive, they have to be homozygous recessive. You're not going to show recessive unless you're homozygous recessive. With dominant, you can show dominant even if you're not homozygous dominant if you're heterozygous. So, okay, the next one, we'll do that one together. It's a continuation kind of this problem where it's the next generation. So, let me erase this one. I don't care. Some of these questions ask, is this Hardy-Weinberg or not? I don't care if you know that. What I care that you know is how to do the math equations part of it, okay? I care that you understand that homozygous recessive and the population, if you've got the homozygous recessive number and the population total, you can find out any of these. As long as you have one of them in the total, you're good, okay? So, let me grab this marker real quick. All right. Okay. Let me move this. Sorry, I'm trying to... My recliner is not the best place to do this, but it's the only spot I got because my son's in here and I can't go in there because I'm afraid he might get sick when I'm not in here. Hey, Nathan. 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 Here, so you can skip the ads while I do this video. All right. So next one, it tells us, number 2, the next generation of lizards has... All right, it has 1,092 individuals with green, which we know green is dominant. So 1092 dominant, but that's all it tells us, is that it's green. So we don't know if that's homozygous dominant or heterozygous. And 108 individuals with blue scales. So 108 is recessive. So we know that the 108 is going to be little g, little g. So add that up. 0, carry the 1. 0, carry the 1. 2, 1. All right, so your total population is 1,200. Total pop. Okay? So you know that you've got 108 here and you've got 1,200 here. So you go 108 over 1,200. So, I don't have a calculator. I've been using my phone. All right. Let me pull it up on my computer real quick. Let me view scientific. Okay. So now you've got 108 divided by 1,200. So Q squared is what we just solved for, right? Because Q squared is this. So 108 divided by 1,200 is 0.09. Nathan, not too loud. And that equals Q squared. Nathan, turn that down, please. All right, so we square root. Q is going to equal 0.3. Okay? Everybody with me so far? So now we've got, let's do our, that's good, buddy. All right, so these are our equations, right? So we go here because we found Q. So we plug Q in here. So P plus 0.3 equals 1. Just subtract 0.3, subtract 0.3. P is equal to 0.7. So P equals 0.7. Okay, so now we plug in P's and Q's here. So P squared. Oh, go this way. This way, actually. All right. P squared plus 2PQ plus Q squared equals 1. So let's plug in P's and Q's here. So, ready? 0.7 squared plus 2 times 0.3 times 0.7 plus 0.3 squared equals 1. All right? So, you got 0.7 squared 0.49 plus, all right, so 2 times 0.7 times 0.3 equals 0.42 plus, we know 0.3 squared is 0.09 from up here, right? So plus 0.09. All right, so now we add these up. So 0.42 plus 0.42 plus.
Mom, can I have those Mario cards?
0.49.
Mom, can I have those for Christmas?
Maybe. Plus 0.09 equals 1. So Q squared, Q, P squared, 0.49, 2PQ equals 0.42. So what these numbers right here what those circled numbers are. Those are the allele frequencies. So the frequency of Q squared, which is homozygous recessive, is 0.09. The frequency of Q, which is one recessive allele, is 0.3. The frequency of P, which is one dominant allele, is 0.7. The frequency of P squared, which is homozygous dominant, is 0.49. So almost half the time they're homozygous dominant. And 2PQ, which is heterozygous, the frequency is 0.42. So almost the entire other half of the time, when they're showing dominant, they're going to be heterozygous, okay? All right. Everybody with me on that? Okay. That's the first two on that one. Let me look and see if there's any other ones that I'm feeling like you need to look at. Again, on 3 and 4, it pretty much does the same thing. Just find the frequency of the alleles. I don't care if it technically falls into if the population falls into being Hardy-Weinberg, because I don't think the next one would, because in the second generation there are more recessives showing than there are dominant showing. So as long as you can find, as long as you have the population total and the number that are showing recessive, you can find out anything. You just have to remember that the number that they give you to start with of population showing recessive is going to be Q squared. Okay? When you divide, when you put the number of recessives over the population total, you have found Q squared. So if you need to find Q, you got to square root that, okay? So let's look at the other set of practice problems. And I'll do some of them as well. All right, so this is practice problem set 2. I'm only going to do one of them, actually, because there are only 3 problems on here. There are 6 problems on that one, so I did 2 of those. There's 3 problems here, so I'm going to do 1. Because the other ones are Punnett squares. Y'all know how to do those. Okay. All right, we'll do this one together, too. So, pardon my awkward writing on this. It's hard to write on a board, keep it where you can see it, and record yourself all at one time. Nathan will actually usually help me, but I don't know that he's up for that. I know you hear him laughing, but...
Mom, if we can go to Caleb's house.
Well, honey, he's a kid on YouTube. Okay, so practice problem on practice problems 2. Problem number 1. You are researching macroinvertebrate diversity in an urban creek, but need to determine the frequency of clockwise shells. So clockwise shells are dominant to counterclockwise. So let's do because of its name, the Hepatogenidae, let's do big H, little h, okay? And those look different. Like big S, little s for shell. S's, they look the same. One's just smaller than the other. So I always try to pick a letter where the uppercase and the lowercase look different from each other. So let's do big H is clockwise. And little h counterclockwise. All right, and so it goes on to say that after several counts from each habitat in the creek, you collect 3/4 that are clockwise. So we take those fractions and we put them into decimals. What's 3/4 of 100? 0.75. So you've got 0.75 are dominant, which means 0.25 is recessive. So if 0.25 is recessive, that means it's little h, little h. So that means Q squared equals 0.25. Okay? All right. So Q squared is 0.25. So That means 0.25. Sorry, I'm trying to use the calculator on my computer. Square root. So Q is equal to 0.5. Okay? This way. All right, so P plus 0.5 equals 1. So minus 0.5 minus 0.5. P is equal to 0.5. So P equals 0.5. So P squared, 2.5, because, you know, it follows logic here. All right, so P squared plus 2PQ plus Q squared equals 1. Okay? Right here. You here for it? All right, so let's plug these numbers in. 0.5 squared plus plus 2 times 0.5 times 0.5 plus Q squared, which is 0.5 squared, should equal 1. All right? So what is 0.5 squared? 0.25 plus, all right, so 0.5 times 2 times 0.5 equals 0.5. And then 0.5 squared again over here is 0.25. All right? So 0.25 plus 0.5 is 0.75 plus 0.25. That's going to equal 1. All right? Are we here for it? Does that make sense? All right, let's look. All right, so for number 3, I was going like 7 over 10, 7/10. Take those fractions, make them into decimals. 7/10, 0.7. 3/10, 0.3. You can determine, let's see, gather your data and observations. You see that 7/10 of them have long tails. So we're going to assume that long, in that case, is dominant because the majority of them have it. So 3/10 have short tails. So 0.3 would be Q squared on that, okay? Have at it. All right. Let's see. All right, number 5. We might do that one together. Okay. Bone configuration of various individuals. However, you notice that 2/4 of the individuals have a bent 5th digit, while 2/4 have normal anatomical position of the 5th digit. What's 2/4? Half. What is half? 0.5. All right. Having a bent 5th digit is recessive, and normally aligned is dominant. So determine the frequency of both of those using the Hardy-Weinberg equations. Okay. So you know that 2/4 of something is 0.5. Okay? So the way that they're asking these questions on this one, it's telling you the fraction, so you don't have to have the population total. On the other one, that's why I did 2 different ones where you had to figure out the population total in order to have the fraction, whereas this one, it's taking out that step for you. They've already given you the fraction of what you need. You just have to turn it into a a decimal. So 2/4 is half. So you've got Q squared at 0.5. Square root of Q. We've just done this one. 0.5 square root. 0.5 square rooted. It's 0.71. All right. So that would make P 0.29 because 0.71 is Q. 1 minus 0.71, 0.29. You with me? It's got to equal up to 1. All right. So, P squared sorry, my Christmas tree's reflecting. Plus 2pq plus q squared equals 1. All right. 0.29 squared plus 229.71 plus 0.71 squared. All right, should equal 1. All right. 0.29 squared, 0.084 plus 2 times 0.29 times 0.71 equals 0.412 plus 0.71 squared. 0.504. All right, so now add them up. 0.084 plus 0.412 plus 0.504 equals 1. All right, so p squared is going to equal 0.084. 2pq is going to equal 0.412. So when you're determining the frequency of alleles, I want the frequency of all of them, okay? I want q squared because that's homozygous recessive. I want q because that is one recessive trait. I want p because that's one dominant trait. I want p squared because that's homozygous dominant. And I want 2pq because that's heterozygous. I want all 1, 2, 3, 4, 5 of these, okay? I want the number for all 5 on all of these problems. We clear? That's why it's all 15 points, okay? All right. If you have any questions about any of this, please shoot me an email. Again, the email iscchandler@shorter.edu. It's not achandler, and it's not at hawks.shorter.edu. It's cchandler@shorter.edu. I'm going to post this and the other one, hopefully at the same time. The study guide video will probably go up first because it's currently uploading while I'm recording this. So, all right. Questions, comments, concerns, doubts, fears, anxieties, give me a call, okay? Or shoot me an email. Have a wonderful Thanksgiving. Bye, guys.